Give them the new link is also been sent out to your emails and updated in the participants outline. Okay, welcome everyone to the Data Science Competition 2021. This competition is brought to you by the NUS Statistics Society, partnered with HP. I'm Claudia, and I'll be your MC for today. Thank you, Prof. Carol Hargraves, guest speaker, Ms. Jamie Neal, HP, and of course, participants for joining us tonight. We are very excited to have all of you on board, and we hope that this competition will be a valuable learning experience for all the teams. Before we start, let me brief you about the program outline. You'll be having the first workshop after the opening ceremony, which is later tonight. The second workshop will be on day 3, and you'll have a few days to work on your solution before the submissions close on day 7 at noon. So it's not 2, 3, 5, 9. We will then end off the competition with the closing ceremony on day 8. So please refer to the program outline that has been sent to your emails for the exact timings. Also, because of the overwhelming response to our event, the live Zoom sessions will be live streamed over to YouTube for participants, where you guys are tuning in now to watch. So if you have any questions, you can just use Pigeonhole to ask us. So you can take out your phone to scan the QR code, or you can just go to pigeonhole.net and key in the passcode, which is DSC 2021. And you can ask your questions there. So you can just access this Pigeonhole Q&A now. Okay. Now, prizes. The top 3 teams will receive a cash prize of 500, 300, and 200, as well as 4 HPE vouchers per team, regardless of your team size, in these varying dominations as shown. And the top 3 teams will actually have an opportunity to do a more detailed code walkthrough with HP after the competition at HP's discretion. For consolation prizes, we will be giving the 4th to 10th teams $100 cash prize per team. And all team members of the top 10 teams will also receive a HP 3D printed badge holder. As for the lucky draw and the free t-shirt, do take note that due to overwhelming response, the free t-shirt and the lucky draw will only be for participants who have both submitted a solution that meets an easily achievable baseline and attend our closing ceremony. So we hope to seek your understanding about this issue. All right, now, without further ado, the president of the NUS Statistics Society, Joel Tan, will say a few words. Joel, please.
Thanks, Claudia. So a warm welcome to all of our participants. Let me start by talking about the general theme of the competition, which is computer vision. So computer vision is a field that has seen just tremendous growth, both in academia as well as the industry over the past few years. To some extent, it is the success of computer vision techniques in very, very impactful practical tasks such as, facial recognition, object detection, even things like medical image analysis, etc. So that is what led to the huge explosion of interest in deep learning and AI in recent times. Now, let's talk a little bit about this competition's problem and data set. Well, personally speaking, right, from the perspective of a student and as an enthusiast, someone who's actually interested in these types of competition as well, I think this particular problem is certainly a very interesting one. So I can already think of like many possible different techniques or approaches to model the problem. And really, unlike maybe some of your school projects or even some Kaggle competitions, where all you do is really just like find some state-of-the-art model, train it, maybe do a bit of transfer learning, maybe do ensembling, and then like voila, what ends up happening is everyone just uses the same few models and the same few techniques, and whoever has the most GPU resources ends up winning, right? We obviously don't want that, and I really don't think this particular problem falls into that. I believe teams that put in more effort in finding creative ways to improve the training data, or even better ways to how to even approach the problem in a modeling perspective, these teams will definitely see improved results. And just a note to the participants, We have done our best to cater to students of various backgrounds and skills. So whether you're a newbie to the field and you know you're here mainly just to explore, just to gain more knowledge in this field, or you may already be like quite experienced in these types of computer vision problems or competitions in the past, and you're really gunning for the top spots or the first prize even. Well, whatever it is, we hope that by the end of this competition, you would have gained valuable knowledge, learning points, experiences, or perhaps even some monetary reward from this competition if you end up winning. Now, I'd like to take just a brief moment to talk about our society, NUS Statistics Society. And I would like to share that for our society, this is definitely the biggest event that we have ever organized in terms of participation numbers. And I'm very grateful for the remarkable contributions over the past months, all the planning, everything involved from each of our members. And I'm just genuinely proud to see the growth of the society just over the past few years. And aside from the competition, we also provide technical workshops, career events, and the likes for the student body, aimed primarily at those who are interested in statistics and data science. Internally, within the society, and as niche as it sounds, we really do aim to like create a family culture. And I really know everyone like uses this term so loosely, but really, we aim to focus on a culture of everyone helps everyone, open sharing, and even learning together. And definitely this is achievable because at the core of it, we really are just a bunch of people who are interested in stats and data science. So if you're currently an NUS student and this society and what it does interests you, do keep your eyes out for our recruitment period next academic year. Typically starts around 1 or 2 weeks before the semester. And for the rest of you, do feel free to follow our social media and to join our Telegram community group if you are not already in it, to keep updated on our future events and related matters. Finally, I would like to really thank our main partners, HP, for their massive contributions in providing a very interesting data set and problem statement, and for their continuous and insightful discussions, communications to improve the delivery of this competition. I would also like to thank our very generous sponsors, Shopee, for their contributions to the prize pool and rewards, as well as the NUS professors, Prof. Carol Hargreaves, which is here today, as well as Prof. Alexander Thierry, who have offered to help out in judging. I would also like to thank all of the members in the organizing team within the society who have definitely worked very hard throughout this holiday period to ensure that the competition became a reality. And finally, from all of us in the organizing team and the society, we would like to send you guys our biggest thank you to all of you, the participants here who are tuned in today, as your very presence here has pretty much validated all of our combined efforts over the last few weeks. So once again, thank you and all the best for the competition.
Thank you, Joel. Next, from our competition partner, we have Ms. Jamie Neo, who is the Director of Engineering. She is a smart manufacturing champion and has been named in the inaugural Singapore 100 Women in Tech list. I will now hand over the time to Ms. Neo. Ms. Neo, please.
Thank you, Claudia. Hi, everyone, and good evening to everyone. It is good to see all of you gathered here virtually this weekend for the NUS Data Science Competition, a student-led event aiming to engage and expose students across different universities and different disciplines to data science. HP is proud to be this year's partner for this competition. First, I would like to applaud the EXCO for organizing this event and pushing it ahead with this virtual setting. The COVID pandemic has indeed changed the way on how we operate, and we'll need to learn how to collaborate remotely in this new normal. Now, let me share a little bit more about HP. Can I have the slides, please, Ashwin? Ashwin, are you able to share the slides? Yes. I'd like to share more about HP. So if you can go to the next slide. HP was founded in 1939 by two engineers, Bill Hewlett and Dave Packard. These two friends shared a vision, inventing a better future for everyone using technology. They put all their money, a little more than $500, and started the company in Dave's unheated dirt floor garage. Do you know why we are called HP? It was decided with a coin toss between the founders, and Bill Hewlett won. The first product is the audio oscillator, an instrument used to test sound equipment, and one of our earliest customers is Walt Disney Studios. Next slide, please. HP came to Singapore as one of the first MNCs investing in local talents as early as the 1970s, growing alongside Singapore. It started in 1970 as a low-cost manufacturing base in a flatted factory at Redhill Industrial Estate. Fast forward to today, we just celebrated HP's Singapore 50th anniversary in 2020 at our HP campus, which you can see here, which houses R&D, manufacturing, supply chain management, sales and marketing with 3,000 plus employees from 35 nationalities. In 2015, Hewlett-Packard split into two companies, HP Inc. and Hewlett-Packard Enterprise. HP Inc., where I'm from, focuses on PCs and printers, while Hewlett-Packard Enterprise focuses on business solutions. Next slide, please. Next, we are from the print business at HP Inc., and we are responsible for the manufacturing of print heads and ink cartridges for printers from home to office to commercial to industry and 3D printers worldwide. You can see on the right, SMART, or it stands for Smart Manufacturing Application and Research Center, where we trial new technologies like 4IR or 4 Industry Revolution technologies at our manufacturing lines. Next, I would like to show you a short video of what HP is all about. Ashwin, if you can help to roll the video. Thank you. HP vision is to create technology that makes life better for everyone, everywhere. And our mission is to engineer experiences that amaze. We value reinvention and making a purposeful impact to humanity. And in the video, you saw some of the sustainability initiatives with HP products made from ocean-bound plastics, recycled plastics, and how some of the newer technologies like 3D is enabling a segment of one in the orthodontics market. Now, back to the challenge for this competition. We would also like you to embody the HP spirit to come up with solutions to make life better for our team in manufacturing. You would have heard, all roads lead to Rome. Yes, there are many ways to arrive at a solution for a problem you have on hand. I look forward to seeing the different solutions that the teams will come up with. However, how you get there and when you get there is also important. In any workplace, there is always a time constraint to solve an issue, and we look for the most efficient way to solve the problem. We can't wait till the cows come home, though they are coming soon, actually this Chinese New Year, the year of the cow. This is where diversity and multidisciplinary team comes in, each contributing their insights, expertise, and experience. It is also important that team members commit themselves to listen carefully, respect the opinions of others, and value other team members' skills and strengths. Finally, I would like to leave you with one advice. Strive to be a T-shaped individual. Know what area you want to specialize or grow in technical depth. This is part of the T. Also invest time in picking up a breadth of knowledge, enough for you to know who and how to form your multidisciplinary team to tackle the different problems in work and in life. Thank you. Stay safe, stay healthy, and be creative. Back to you, Claudia.
Thank you, Jamie, for the in-depth and interesting explanation about HP. Next, we'll be talking more about the problem statement. I will now pass the time over to HP and my teammate Ziming.
Hello. Hello, Claudia. Can you go to the next slide? Hi, good evening, everyone. I'm Ethan from HP. So next, allow me to introduce briefly about the business context. Let me start with HP Singapore. HP ink cartridge manufacturing started in Singapore since 1970. Actually, we just celebrated 50th anniversary last year. Currently, there are around 100 manufacturing lines managed by HP Singapore team, which contribute hundreds of millions of volume every year. Those products will be shipped to the whole world from Asia Pacific to Europe and America. Now, HP Singapore continues to contribute through digital transformation and innovation for our people, our customers, and businesses. We are in a significant transformation from traditional manufacturing to a new age smart manufacturing or fourth industrial revolution by adopting smart and autonomous systems fueled by data and machine learning, deep learning, or AI techniques in general. Next slide, please. So the problem that we are going to present today is aligned with this direction. Basically, we would like to use algorithm to optimize or replace our current process. The whole problem starts with a very small component called equipment. If you can look at the image on the left. The equipment is one piece of gold-coated metal chip attached on our cartridge, which carries some confidential information owned by HP. So during our normal manufacturing process, there are some parts will be rejected or scrapped because of they cannot meet our quality standards. Those equipments on the cartridges will be peeled off and pasted on a paper before the proper disposal process. And as aforementioned, because of the value and sensitivity of equipment, we need to ensure that every single equipment is properly accounted for and disposed. Therefore, usually HP staff will carry out an audit process for those equipments on the paper. I think the photo is covered, but currently this audit process is very manual. Our staff need to travel all the way to factories and sit there for hours to count the equipment on the paper and find anomalies, such that it can ensure that the actual counting of equipment is tallied with the record counting. As you can imagine, it's a very repetitive, tedious, and time-consuming process. And currently with the COVID situation, it's even challenging because of a travel restriction. So we would like to get your talent and help to develop an automated vision system to replace the current manual audit process, such that we can enable the virtual audit by just using the image of the photos of those equipments. And definitely, this system will improve the efficiency and ergonomics for HP employees, such that they can move to more higher value work. So we are looking forward to your solutions. Okay, back to you, Claudia.
Thank you, Ethan. Now my teammate Ziming will continue introducing the problem.
Hello everyone, I'm Ziming and I will be introducing the problem statement. The problem statement is object counting, handwriting recognition, and anomaly detection in equipment chip images. Your task is to design a model that is able to, number one, identify the number of chips present in each counting paper. Number two, identify the handwritten manual count present on each counting paper. And lastly, number 3, discover and indicate the location of anomalies. Here is a sample picture of the counting paper and chips. You can see the arrangement of the chips and the handwritten count at the bottom right. Note that the handwritten count is not always accurate. Next. As mentioned before, there will be anomalies in some of the images. There are 2 anomalies that you need to account for. The first is double stacking. This refers to the overlapping of 2 chips. You should include these overlap chips in your object count. The second anomaly is black dots. Some chips will have black dots on them, and you should not include chips with black dots in your object count. Here are some examples of the anomalies. Do take note of each images. Do note that some of the chips with black dots around them, like the image at the bottom right, these do not count as anomalies. Black dots are only considered when the dots are on the equipment chip itself. In the case of the dots surrounding the chips, they should be counted as regular chips. Here are some examples of the chips that may look like anomalies but are not. Examples include defects or breaks and black epoxy glue. Note that the black epoxy glue is not counted as black dots. All of these should be counted as regular chips. And before I move on, do note that such anomalies are very rare in the data set, so you have to pay careful attention to find each of them, as there's not much training data based on these anomalies. Now, moving on to the judging criteria, there will be 2 rounds of evaluation. The qualifier rounds is applicable to all teams. Each team will be evaluated based on the accuracy of their submission. The evaluation matrix will be shown later, and the grading of your submissions will be done automatically on our end. Based on the accuracy of your models, we will select the top 10 teams to advance to the next round. The top 10 teams will be notified and they will need to prepare a slide deck, which they will then present to our panel of judges. The judging criteria will be shown later as well. This is the evaluation matrix for the qualifiers. We will use binary to evaluate your object count and handwriting recognition. So you either get it right or wrong. There's no in between. We will use the mean average precision to judge the accuracy of your bounding boxes. The bounding boxes is used to indicate the location of each anomaly that your model might have predicted. The top 10 teams will be chosen using this evaluation matrix, and they will progress to the final round. This is the judging criteria for the finals. The teams presenting will be judged based on the clarity of their presentation, the creativity of their models, their model performance, the completeness of their solution, and how easy it is to use their solution. Once you are ready to submit your solutions, you can email your submissions to us. Note that only 1 submission is required for each team. The link to all formatting details will be made available to you soon. All instructions and datasets will be provided on our Kaggle platform. You can use the Kaggle platform to test the accuracy of your models. However, Kaggle submissions will not count as your final submission, and it will not be considered for any of the prizes. Only submissions emailed to us will be considered. That's all for the problem statement. If you have any questions, feel free to post them in the pigeonhole. Here is the link to the competition. I'll give you a few moments to open it up, or you can scan the QR code as well. Okay, I'll hand my time back to Claudia. Thank you.
Okay, thank you, Ziming. Since we have a little bit of time left, we are going to entertain some questions. So if you have any questions for the HP team, you can write down your questions in the pigeonhole, and I will pick the most popular questions for the HP team to answer. And if you have any other important queries regarding the logistics or how you should submit, you can email us at our email. And the link to these slides will be updated in the participants outline that you guys have. And you can also follow our socials to keep up to date about our events. So we have an Instagram account and we have a LinkedIn account. So once again, if you have any questions that you think are worth mentioning, you can put it in the pigeonhole and we will let the HP team answer some questions. I see that the YouTube chat has a few people asking for the Kaggle link to be pasted there. So maybe you can do that. So we will be sending all the links, including the ones with more technical details on submission, the judging criteria, and all the important stuff through email after this live stream and after your workshop tonight. So this includes stuff, includes more information about the anomalies and what you should consider when you're making your model. All right, so I see quite an important question on Pigeonhole. Someone asked, how do you define an anomaly, like for double stacking? Does the bounding box need to be fully covering both chips or just the overlapping area where the chips are double stacked? And as for the black dot, should the bounding box be only including the black dot or should it be including the whole chip? All right, so maybe someone from the team can take this.
Well, so based on how the data set is labeled currently, our bounding box is fully covering both chips. So it includes both chips inside. And for the black dot, it is the whole chip including the black dot. So I'd like to highlight that there is only, and this might come as a shocker to most of you, there will only be one black dot and one double stack training example. So wow, you might be thinking, oh, that's crazy. How are you gonna train a model with just one image? And that's where the creativity has to come in. So later in the workshop, we will be sharing techniques such as data augmentation a little bit. But in general, there are ways to definitely create or generate your own training samples based on this example. And that is something which we expect the students to do. And it's definitely something that's worth learning. Yeah.
Okay, I see another question. Is it possible to win the competition using just Python?
Okay, I can answer this. So of course you can use Python to answer this. In fact, you can use anything actually, as long as you can complete and produce an output. and predict the model itself, anything goes. However, we still strongly encourage you to use Python because it will make the running and the testing, everything would be much smoother and easier. So to answer your question, yes, of course, you can use just Python.
Maybe I see a question on what is the baseline, right? So people are asking exactly what are the baseline. So I would like to share that we don't want to reveal the baseline because we don't want people to use, the idea of the baseline really is to make sure that you guys aren't just like using random guessing or just putting or submitting a solution with just all zeros, things like that. So don't worry, the baseline is definitely going to be achievable. And as long as you solve at least one of the three problems, most likely you have already met the baseline, right? So in my opinion, probably the easiest one to solve is the handwriting part. And even the object counting part, there are some very basic things without even including the anomaly. But we, of course, if you want to win the competition, you want to get to the top 10, of course, you will have to deal with the anomalies. And that is, I think, the most interesting part of the challenge. But if your sole purpose of joining is really just to meet the baseline, just to get the free shirt, the certificate of completion, things like that, then really the amount of effort that you need to put in might not be that much, right? So of course, you will still need to put in effort. You will still need to train a model. So if you have never coded before, this will definitely come as a learning experience. But I think at the end of the day, it is definitely achievable, even for someone who is a beginner.
Someone is asking about the test statement, which will be released on Friday, 9 a.m. So, Jimmy, you want to take this?
So regarding the test set that will be released on 9 a.m. on Friday, we hope that your team will be able to produce or at least train your model by Friday, so that when we release the test set at 9 a.m., you can quickly use your model to predict the output and the count of the test set that we provide to you, and then email in that output to us by the deadline on Friday, 12 p.m.
I see another question. Can we expect the test set to be under similar environmental conditions? So this refers to lighting, orientation as the training/validation sets.
That's a very good question. So the test set will definitely be in similar conditions. So the test set is particularly tricky, but it is only tricky in the sense that there will be more errors in the test set, or more anomalies, in the test set. There will be more cases where your handwritten count does not match the actual object count. So you can't cheat by using like the handwritten count, just use the handwriting prediction to get your object prediction. So there will definitely be more cases where they don't match. So generally there will be, in the test set, it will be more tricky in that sense, but in terms of the images themselves, they will be taken of similar quality as the ones that are in the training set. And more importantly, the anomalies will be very similar to those in the training set. So those of you who are more familiar, you might be already be thinking of ways to do augmentation, things like that. So yeah, definitely it will help. And don't leave the live stream, by the way. There is a workshop coming after this. Just for those who are not aware, yeah.
Okay, so thank you to Ming, Joel, and everyone who answered the participants' questions. Again, if you have any more questions, the Pigeonhole link will be active until next Saturday. So at any point, if you have any more questions, you can ask your questions there or you can email us. All right, so the opening ceremony has now come to an end. Thank you for staying with us, and we hope that you will continue to stay tuned because your first workshop will be coming right after this. So now we will be handing over the time to Society's workshop team. Thank you, HP, professors, and participants for joining us tonight once again. Thank you.
Thank you. All the best.
Thank you. All right, Jet, take the stage.
Green. All right, we will start at about 7:50. The time now is 7:48. So take a short break, get prepared, because this workshop would take around 1 hour and 45 to 2 hours. So yeah, we'll continue at 7:50. Okay, the time now is 7:50. Let's get started. Okay, welcome to the Data Science Competition Workshop, Workshop 1, Applied Computer Vision. This workshop is presented to you by the NUS Statistics Society. And our presenters for today will be Georgie, Rama, Agatha, and Yi-Zhe. So there will be another workshop by Up Level on day 3, and that will also be relevant to the competition. So who are we? Let me first introduce NUS Statistics Society to you. We are under the Department of Statistics and Applied Probability, and we are committed to foster a community of students passionate about statistics, data science analytics, machine learning, and quantitative finance. But we are open to all students of any background, experience, and interests. Do stay connected with us and see what ways we can work together. Let me introduce you to our upcoming events. You can keep in touch with us in the following social channels. Our Statistics Society website is where you can find resources of all past workshops, slides, recordings, upcoming workshops for this semester, and etc. So that means that for semester 1, you can receive all the resources as well. Our Telegram chat is where you can talk about all things under the sun, relevant topics, of course. Our Instagram is a place for broadcasting events, memes, statistical musings. Do check us out there. LinkedIn for serious content, and finally, our email if you'd like to connect and collaborate with us. So what workshops do we have this semester? First, we have the Data Science Competition, Applied Computer Vision, which is today. We will be having an effective data storytelling workshop on Wednesday, 27 Jan at 6:30 p.m. to 8 p.m. We'll also be having using Tidyverse in R for data analysis and visualization. So this Tidyverse workshop would be on 4th of February, Thursday, conducted by our Statistics Society members, Sanraj and Jianhui. To learn more about it, check out the Statistics Society website here. So the DSC workshop by Up Level will be on day 3, 18 Jan, from 7 p.m. to 9:30 p.m. It will be an image task related workshop, and therefore it is an object detection and counting workshop. So So that it is titled Using Computer Vision for Object Detection and Counting by Jackie Tan, co-founder and CEO for UpLevel. Now, finally, welcome to our workshop. Introducing you to our workshops team, I'm Jet, I'm the Director of Workshops. We have here Ming Liang, Peng, Michael Ng, and Michael Yang, who will be presenting the Effective Data Storytelling Workshop. Today, Rama, Agatha, Georgie, and Yize will be presenting today's workshop on Applied Computer Vision. Rama and Georgie are studying computer science, Agatha is studying statistics, and Yize is studying data science and analytics. To learn more about workshops, you can click the link here. Now, welcome to the start of our workshop. Before I hand over to Rama, the first presenter of today, the slides can be found at this link over here. So let me send this on the YouTube. I can't send the link. Okay, take a short moment to record down the link and you can follow through with the slides if you like. These slides are also available on the workshop's website. So the workshop, the Statistics Society website. So the society website is the main one that you need to refer to, which is available here. If possible, someone can help to send this link on the YouTube chat. All right, let me now pass the time to Rama, who will bring you through today's workshop.
Thank you, Jet. Hello, everyone. In today's workshop, we will be teaching you all about computer vision and deep learning. I will first start out with an introduction to a traditional computer. Thank you, Jet. Hello, everyone. In today's workshop, we will be teaching you all about computer vision and deep learning. I will first start out with an introduction to traditional computer vision, and then go through some code that's used in computer vision. Agatha will explain the convolutional neural networks in deep learning, followed by Georgie, who will take us through transfer learning, which is a technique used in deep learning. And finally, Yize will be sharing some useful tools and resources related to machine learning. So, what is classical computer vision and deep learning? In the past, people always used traditional computer vision techniques that are more manual methods for extracting features from an image through specific image processing algorithms and methods. So when you first started on a computer vision task, you would go about it by detecting colors, edges, and objects. And as the resulting features would be human engineered, the reliability of the model depended directly on the methods that you chose to use for feature extraction. And then came along deep learning. Deep learning offered a significant increase in performance and accuracy gain for computer vision tasks. And this is because deep learning models have millions of parameters that the computer generates for you in a neural network. Ever since then, traditional computer vision techniques have sometimes been thought of as relatively older or outdated, and also more laborious for humans. However, I'll be explaining to you why these classical computer vision methods still have a very important role today, and why and when they can even be better than deep learning. So the first reason would be efficiency. Deep learning is sometimes unreal, as computer vision techniques can solve the problem much more efficiently than deep learning. Many computers like color thresholding and pixel counting.
You can switch. You can turn off the Google Meet because the audio is lagging.
Sorry about that. Can everyone hear me? Okay, so Many computer vision algorithms like color thresholding and pixel counting are not class specific. So this means that they are very general and can perform the same for any image. And in contrast, features learned from a deep neural network are specific to your training data set that you use to train the neural network. And they may not perform well for images that are of a different kind from your training data set. So, for example, we're classifying two objects as red or blue. A deep neural network, given you give enough data to the model for it to learn, so maybe thousands of images of red images and blue images. However, it can be achieved through a simple color filtering with classical computer vision. So sometimes traditional computer vision offers a much simpler and much faster solution. The next reason would be transparency in computer vision algorithms versus a black box in deep learning. So if the data set you use to train your deep learning model is very limited, for example, the training data may not be able to generalize and may perform poorly on new unseen data. So it would not work well for the current task at hand. And it would be very difficult to manually tweak the parameters of the model because a deep neural network has millions of parameters with complex interrelationships. So in this way, deep learning models are considered a black box. But on the other hand, traditional computer vision algorithms can be tweaked by the engineer to perform better in case there are any problems that crop up. Sorry about the audio. Is it still lagging? Okay, perhaps I can turn off my video so the audio can be clearer. Okay, I hope it's better now. So the ideal approach would be to use a hybrid of traditional computer vision and deep learning. So this works in high performance systems which need to be implemented quickly. So for example, you're building a security camera. A computer vision algorithm can efficiently detect faces or other features or moving objects in a scene. And then these detections can be passed into a deep neural network for object classification or identity verification, for example. So in this way, the neural network only needs to be applied on a small patch of the image, allowing us to save significant computing resources and training effort, compared to if the entire image frame had to be processed by the neural network. I'll now be explaining some common steps that you would do in computer vision tasks and how to go about doing them in code. We'll be using the OpenCV library in Python, which is the library meant for computer vision tasks. So if you click the link here, it will bring you to a folder where you can see a Python notebook. So you can right-click and open it with Google Collaboratory. And for those who don't have Google Collaboratory, you can download the file into your computer, go to this website, which is a Google Colab website, click upload your notebook there, and it would automatically open after you upload your notebook. So you would see something like this. So we first start out by importing the libraries that we will be using. So CV2 refers to OpenCV, and we will also be using NumPy to process the image arrays, and Matplotlib to visualize the images. So to read images into OpenCV, you use the cv.imRead function and pass in the image that you want. And if you click print, what it would give you is the array that represents the image. So if our image is a black and white image, it would be a two-dimensional array. But if your image is colored, you would have 3 color channels, and hence it would be 3-dimensional. So we can then use matplotlib plt.imshow to visualize the image. So you would notice that something looks off in this image. And this is because the original image looks like this, where you can see the sky is blue, but over here, the sky appears to be orange. And the reason for this is because the image loaded by OpenCV is in blue, green, red mode, while matplotlib displays it in red, green, blue mode. So to solve this problem, we need to convert from BGR to RGB, which is known as converting between color spaces. So to do this, all you have to do is cv.cvt color, pass in the image and what you want to convert it from and what you want to convert it to. And now the image looks as per the original image. And you can do the same to convert it to black and white by passing BGR to gray. Now I'll be going through resizing and rescaling frames. So many deep learning models require that our images are of the same input size, but the raw images that we collect when we are creating our data set may vary in size. And this is why we need to do resizing and rescaling. And many machine learning models can also train much faster on smaller images because there are fewer pixels to be processed. So if you do image.shape, you will see the dimensions of your image. The first one refers to the height, the second refers to the width, and the third refers to the number of color channels. So 3 over here since it's a colored image. We can resize the image by using cv.resize and enter the final dimension that you want it to be. But as you can see, the image looks distorted as the aspect ratio wasn't maintained. So to solve this, you can define a function that rescales the image to the exact same aspect ratio. So what this does is it scales the width and the height by the exact same scale, and then uses that dimensions to resize it. So then you can see that the aspect ratio of the image is maintained. You can also crop the image by choosing a subset of the rows and the columns from the image array. Next, we have image blurring and smoothing. So when you blur an image, you remove outlier pixels that may be noise in the image that may cause the image model to learn incorrectly. And this is a common operation that you perform before tasks like edge detection. So there are a few different types of blurring: average, median, and bilateral. So how it works is average blurring. You specify a kernel area. So for example, 35 by 35. So if it's a 35 by 35 square here, what the algorithm does is that it takes the average of all the pixels within this square and replaces the central pixel by that average. So as you can see, the image is blurred, but you can see that the edges are not preserved and the edges have been blurred out too. So to improve this, we can instead use median blurring. And what this does is that instead of taking the average, it takes the median pixel value within that kernel size. And you can see that here, the edges are a lot less blur, but it's kind of still diluted. So to improve this even further, we have a method called bilateral filtering, which ensures that the edges are sharp, like this. So how this works is that it compares the difference in pixel intensity within the kernel. So if two pixels have only pixels that are of similar intensities will be considered for blurring. So if you're at an edge, you can see that the pixel intensity would be very different. So they would not consider it for blurring. So this would ensure that the edges do not get blurred and hence will remain sharp here. And there are a few parameters here that you can play around with, and you can find out more from the OpenCV documentation. Next, we have image transformation. And this is done as part of data augmentation, which is a technique that's used to increase the amount of data in our data set by adding slightly modified copies of already existing data. And this is very useful when your data set is small to begin with, or if most of the images in your data set are of a similar type. So to get more data, we would just need to make minor alterations to our existing data set. And minor changes like flipping, translating, or rotation will allow us to increase the quantity and variety of our data set. So for example, you would want this dog and an upside down dog to both be classified as a dog. So regardless of the orientation. And this is why you need to show the model different orientations of the same image. So for flipping, you can do it by using cv.flip and passing in a number here that represents the orientation of the flip. So number 1 would flip it horizontally across the x-axis. 0 would flip it vertically across the y-axis. And -1 would flip it both vertically and horizontally. We can also translate our image by defining a translation matrix, defining a function that will wrap a translation matrix around our image. Yep. And you can also do rotation in a similar way. So you can see that over here, the image has been rotated around the center. And you can instead also rotate it around a specific pivot by specifying a pivot coordinate. But take note that the rotation function and the translation functions are functions that we have defined and are not given by OpenCV already. Next, drawing on images. This is very useful when you're doing object detection and you want to draw a bounding box around the image and have a label. So to draw a line, you do cv.line. You pass in the image on which you want the line to be, the starting and ending coordinates of the point, as well as the color and thickness. You can also draw a rectangle in a similar way by passing in the coordinates of the top left corner and the bottom right corner, and then the color and thickness. And similarly for a circle, you can pass in the coordinates of the center and then the radius of the circle. And if you want to color in the circle or the square, you can enter thickness as -1. And finally, you can also add text in a similar way by specifying the coordinates, the font style, the font size, color, and thickness. Now we have bitwise operations, and this will come in handy when we do masking of the images in the next part. So what I'm doing here is to generate the rectangle and the circle that we will be using to illustrate the bitwise operations. So to do bitwise n gives us the intersecting region between the circle and the square. So all you have to do is bitwise _n and you pass in the two images. Bitwise OR gives us the union of both images. XOR gives us the non-intersecting regions, and bitwise NOT gives us the complement. So now we have masking. And the purpose of masking would be to create, to extract just a specific component of our image. So for example, we want to get just this area of the dog that corresponds to the shape of the mask. So what I'm doing here is creating the mask of a random shape. And then using bitwise.end and passing the random shape under the parameter mask. So this will then overlay the mask on the image. Now we have edge detection. And edge detection is used to find boundaries of objects and images, and is useful for feature extraction and for image segmentation. The most popular algorithm used is called the Canny edge detector that passes the image through a series of steps in the algorithm, which you can read about in more detail from this website. But basically, what it does is it converts the image into something like this, where the edges are drawn out. So you can pass in the image into cv.kenny, and there are a few parameters that you can play around with that are kind of like a threshold that determines whether or not something is considered an edge. So you can see that over here, when I increase the threshold, there are fewer things that are flagged out as an edge. So this would, you can like custom make it based on whatever problem you're trying to solve. And previously I had talked about bilateral filtering, which reduces noise in your image. So you can perform bilateral filtering first to remove noise, and then perform edge detection. So that, for example, over here, every piece of grass won't be detected as an edge. So over here, I'm performing bilateral filtering, and then putting the image through the edge detection algorithm. And if you compare the original image and the final image, you can see that after bilateral filtering, after having reduced some noise, the edges are a lot better defined. Yeah. Next, we have template matching. And template matching is when you're finding small parts within your image that match a template image. And doing template matching is sometimes a simple solution for object detection, and it's a lot simpler than building a whole neural network. But this only works if the objects you're trying to detect are very similar to the template image. And this might likely come in useful for this data science competition. So over here, I'm reading in the images that we're going to be using, the main image and the template. So we'll be using this image and finding occurrences of this template within this image. So what we will be doing is to slide this template pixel by pixel across the image. And then for each position of the template on the image, there will be a similarity metric that's computed. So the result will be a grayscale image where each pixel denotes how much that neighborhood matches the template. So the more white an area, the more similar it is to the template. So you can see here that there's a distinct white spot. So this means that the template is most likely to be found in this area. And this dot, the coordinates of this dot refers to the top left corner of the template. So we can get these coordinates by passing this through a function called cv.minmaxLocation, which will give us and then what we would be interested in is the maximum value, as well as the location of the maximum value, which is the top left coordinate of the template. And why this will be useful is when you're drawing the bounding box around the image. So now that we know the top left corner, in order to find the top right corner, in order to draw the rectangle, all we need to do is add the height and add the width to this point to get this point, so we can draw this rectangle. Yep. And the maximum value would be important because you might, if you have multiple occurrences of a template in your image, you might have a threshold beyond which it's considered that the image is there. And you can create a function that draws many bounding boxes around every occurrence of the template. And finally, we have histogram computation and equalization. So when we're going to compute a histogram that represents the distribution of pixel intensity in the image. So by equalizing the histogram, what we will do is to improve the contrast in an image. And this is important because low contrast images degrade the performance of image processing systems because certain details are not very clear. So let's take, for example, this image. You can see that in the bottom half, the contrast is quite poor and you can't really see the fine details in the image. So we can calculate the distribution of pixels by using cv.calcHist. And you can see here, and it will give you this graph where the x-axis refers to the pixel intensity and the y-axis refers to the frequency of pixels occurring at this intensity. So you can see that most of the pixels lie within the 50 to 70 range. And for the other intensities, they are quite underrepresented. So if we now perform histogram equalization, you should see that the range will be broadened. So you can equalize the histogram by doing cv.equalizeHist. And you can see that the histogram that's returned is a lot more balanced and spread out. And the image that results from this has a much higher contrast. As you can see a lot more detail in this image compared to the original image before equalization of the histogram. Yep, that's all I have for my part. And now I'll hand over the time to Agatha, who will be explaining convolutional neural networks.
Okay. Thank you, Rama. So I'll be going through convolutional neural networks. So first, why is CNN? So deep neural networks are powerful function approximators, but due to the employment of so many parameters, deep neural network often is very sensitive to overfitting. Additionally, deep neural networks cannot handle variations such as translations, rotations, and eliminations in images. Therefore, to tackle this problem, we developed a deep learning algorithm called convolution neural network, which is also known as CNN. A CNN is able to successfully capture the spatial dependencies in an image through the application of relevant filters. The architecture performs a better fitting to the image dataset due to the reduction in the number of parameters involved and reusability of weights. In other words, the network can be trained to understand the sophistication of the image better. What is a CNN? CNN is a very powerful neural network tool. It has a very wide range of use, but I believe it is easiest to explain through its application in image recognition. We can imagine CNNs as automatic feature extractors from the image. If we use the algorithm with pixel factor, we will lose a lot of spatial interaction between pixels. On the other hand, a CNN effectively uses adjacent pixel information to effectively downsample the image first by convolution, and then uses a prediction layer at the end. So if you see a picture here, you can immediately recognize what the picture is. That's because the brain recognizes it as a distinct object and immediately classifies it as a dog. So how does our brain recognize the picture above as 3 dogs in a field? First thing we do is recognize the sharp edge between the green of the background with the brown of the dog's fur. With this, we can recognize a general outline of a dog, which is a long body, not so tall, and 2 ears sticking out. Other shapes inside of this outline help us determine that it is a dog rather than a fox. Consider the tongue, shape of the mouth, nose, and color. So assuming that we want to approach the problem of recognizing shape, just like a human does, we may want to start with making an algorithm that will recognize certain shapes or edges in an image, and this is the convolution and pooling in CNN. And so to sum up the structure of a CNN, we first input an image, then perform convolution operation to get an activation map. After that, we apply the pooling layer, followed by an activation function, then flatten the last output into one linear factor. The factor is then passed to a fully connected artificial neural network. The fully connected layer will provide a probability for each class that we're after. So yeah, next we'll be looking through the convolution layer and pooling layer of a CNN. So before we get started with the convolutional layer, we need to understand filters first. A filter is a specific shape that we want to extract from the picture, like the one right here. You can see right here. Let's say we want to detect a curve like this, like the one in the picture. The curve can be represented using a matrix of values, or we can call it a filter. It is also referred to as neuron or kernel, and the depth of the filter is always equal to the depth of the image. So now we want to test if the image contains this shape, so this image right here. If we focus on the section of the image with the same dimensions as the filter, we can calculate a dot product of the image section values and the filter values. So first, let's look into an area of the image that contains the shape we are testing for. The area we focus on is called the receptive field, so it's this one. The dot product for this section computes to 218535, which is a very large number. This number would be less if the shape does not match the filter shape. So here's one of the examples where the dot product will be of a lesser value. It's because the shape does not match the shape of the filter. In other words, the greater the result of the dot product is, the more similar the image section and the filter is. Therefore, we can use a dot product of the filter and a section of the image to test where specific shapes are located. Getting the filter values correct is important since you want to test for appropriate shapes. The values that we train in the CNN is the matrix value of the filter. So the result of the dot product is then stored in an activation map. Next, we'll be looking through the pooling layer. So the purpose of a pooling layer is to reduce the spatial size of the activation maps. This not only reduces the amount of computation necessary, but also protects against overfitting. The idea of pooling is very simple. We want to reduce large matrices to become smaller ones. The most common pooling technique used is max pooling. The idea of this method is to keep only the maximum value in smaller regions of the activation map and getting rid of the rest. In the orange region above, so this orange region above, the maximum value is 7. So it is kept while 5, 3, and 2 are thrown away. Here's the result, like 7 is kept. Yeah, this is pooling. Okay, so next we'll be going through visualization of a CNN. Okay, so we can change the input size to simulate the size of an input image. So here, the input is like 5, and then the output is 5. I'll also link this link down on the YouTube chat so you guys can try it out yourself later. Okay, so yeah, you can see the input size, we can change it. Then kernel size, then we can change the kernel size, which is the filter. If we increase the kernel size to 2, the filter will have 2 times 2 dimension. So it's the one here. If we increase one more, if we increase one more, yeah. So as you can see here, it's going to have a 3 times 3 dimension. Now, by increasing the kernel size, the dimension of our output or activation map is reduced. So this is now 3 times 3, while the input is like 5 times 5. To retain the dimensions of the output image, we use padding. So if I increase the padding, yep, you can see here, like input is like 5 times 5, and output is like 5 times 5 also. So padding adds 0 around the edges of the input. Like make sure the input and output has the same dimension. So lastly, stride. Stride indicates how many pixels the kernel should be shifted over time. Sorry. Yeah. So if you see here, if the stride is 1, you can move it like 5 times. Like it only will move 1 box. But if I increase the stride, it skips 2 boxes directly. This is what it does. Okay. So now we'll be going through the Keras API of CNN. It's one of the things we can use for CNN. So here you can see compile. Compile is to initialize the model. And fit here is to train the models using the input X, and then we'll give you out like the output of image Y. Evaluate is to measure how good the model is. And lastly, we have predict. So we use this using the model to predict. Yeah. And for this one, this is the code for convolution. 32. So 3 times 3 will be here, the kernel size, and 32 for filters. And the input shape here, 32, 32, and 3. And this is also for the code for pooling. So if you want 2 times 2, you just put here 2, 2. Yeah. So to summarize what we went through just now, in an image task, we want to do feature extraction before classification. Prior to neural networks, feature extraction was done using classical computer vision, like how my friend Rama just explained. But now we use automatic feature extraction via convolutional neural networks. Automatic feature extraction or feature learning is where the convolutional and pooling layers comes in. Afterwards, we feed the extracted result into the neural network to predict the output. So this makes it an end-to-end image model. Okay, so this wraps up my part of this CNN. I've linked also some resources down below, like in the slides. You guys can check it out. It's a very good resource to learn CNN if you're just a beginner, or like if you want to read up or refresh. Yeah. Let's take a 5-minute break before we proceed to transfer learning. But, yeah. Georgie, my friend, will be taking over for the transfer learning part. Thank you.
Yeah, we will proceed at 8:35. So take a chill pill. There's only around 1 hour left. There is no notebook for the Keras. Yeah, that was just a short introduction to the Keras API. If you have any questions for what has been covered so far, you can feel free to ask on the YouTube chat first. Okay, someone asks, what if I have no idea what's going on? How would one start? So I would suggest that you can take a look at Kaggle. Kaggle.com has a lot of competitions, past competitions where the community shares code in the form of notebooks, Kaggle notebooks, where you can see their approaches, you can see their code, see what kind of computer vision techniques that they use, and how they perhaps form a convolutional neural network specific to that competition task. So many of us start off with Kaggle competitions to learn the practical side of doing such deep learning tasks. So Kaggle is one way that you can get started. So you can get started in any approach. So what we just shared is how a convolutional neural network, the idea of it, how it works. We also shared some classical computer vision techniques that you could use for something like data augmentation, because the training data set is quite small. So you likely need to do some data augmentation to improve the performance of your model. So you can get started by getting familiar with how to perform data augmentation. You can read up on some deep learning APIs like Keras, TensorFlow, or PyTorch to take a look at how to use their functions for neural network training. Yeah. You can also wait for the second workshop to get started. The second workshop would cover things like more related to image task. So for example, how to perform object detection, how to perform object counting. So that will be covered in the second workshop by up level. All right, it's 8:35. Now we'll hand over the time back to Georgie, who will teach us about transfer learning.
Thanks, Jet. Okay, it's time for transfer learning. But before I talk about transfer learning, let's all imagine that we're in the movie Alien vs. Predator, and you have built an auto-turret with state-of-the-art NVIDIA GPU and camera guarding your base against aliens, also known as xenomorphs. Also assume you're the only survivor in your base and that you need to sometimes leave it to gather resources, or you may be asleep. Aliens know that, and they may come to attack. Of course, your auto-turret can just shoot any damn thing it sees and kill all the alien attackers. However, harmless predators may come by out of curiosity and may even kill the aliens for you. You don't want your auto-turret to gun them down as well and make enemies with them, so you can't set it to rampage mode and shoot everything on sight. So what can you do? As someone who's into data science, you'd probably build an image recognition model for your turret, so it only shoots aliens. But there is a problem. Building such models from scratch requires tons of data. We're talking millions of images per class. So we need millions of images of different xenomorphs and predators to train this model. But clearly, even with the CCTVs around your base, it's not feasible to gather that much data. At most, you'd have 1,000 xenomorphs and predators in your dataset. So what can you do? Are you going to start war with the predators and make another enemy in the land you're stranded in alone? Fret not. That's where transfer learning comes in. This is when we use another model, called the base model, as a starting point for training our model. We typically pick a base model that has been pre-trained on a huge dataset, similar to the task at hand. For instance, we can use a ResNet 50 base model, which has been pre-trained on millions of images of different classes as a starting point to build our alien predator recognition model. ResNet 50 is basically a convolutional neural network that is 50 layers deep with a certain architecture. We wouldn't need as much data to train our model this way, as we're essentially transferring the knowledge from a pre-trained one to our task. But before I go into more detail about transfer learning, I think it's apt to talk about feature extraction, as it can help us understand why transfer learning works. Feature extraction is essentially the process of extracting quantifiable data from an image, unique to the object we want to identify. For instance, to identify a motorcycle, A feature extraction algorithm may extract the two wheels, the fairings, the cowl, the handlebars, and the exhaust pipe. In a machine learning process, when we pass in an image to our feature extraction algorithm to generate a feature vector, a fixed size array of real numbers, we then pass it into something known as a classifier. We pass this vector into a classifier. And a classifier is an algorithm that takes in input data and maps it to a specific output category. For instance, a cat, a dog, or maybe the type of motorcycle you want to classify it as. And how does it know actually what category to map it to? Well, you first have to train it with labeled input data. And labeled means that for each input data, for each X, you know the Y, you know the correct output. So training is basically the process of passing in these labeled input data, having the classifier predict the output labels, comparing the predictions of the classifier with the correct output labels that you already know in advance, and updating the classifier weights such that the error or the loss function is minimized through a process known as gradient descent. So just repeat it until you have satisfactory results. You can think of it as doing a ton of practice papers until you're ready to take a real exam, hopefully with minimal mistakes or errors. Generally, we can do feature extraction via statistical methods or deep learning methods. In statistical methods, we employ manual feature extraction using a suitable feature extraction algorithm that is chosen using domain knowledge for the task at hand. For instance, we can use a corner or edge detection to detect a door on a car. We then will feed the produced feature vector into our classifier to train it as described earlier. On the other hand, in deep learning, our neural network actually automatically extracts features and learns their importance by adjusting the weights of connections between layers of neurons through backpropagation. We don't specify any feature extraction algorithm. We just let the neural network decide which features to extract and how to assign importance to each feature to minimize the error or the loss function. So basically, we have an image that passes through layers of our network, each layer responsible for a certain operation, as Agatha has described, before encountering the final layer, which is typically a fully connected classifier layer. Fully connected means that it takes in all the outputs of the previous layer as input. The output of this classifier is the probability of the image belonging to each class. In this case, there could be a 95% probability that this image is classified as a 2, and maybe like a 0.51% for the others. But either way, they all have to sum up to 100% or 1. Of course, when you train this model, the answer at first could be wrong. Maybe you have a 50% probability that's 2, or maybe like 40%, and you have like a maybe like a 50% that is 8. Oh, that's not good, that's wrong. So during training, the answer could be wrong. And this error actually is propagated backwards to previous layers via backpropagation to update the weights and the biases of the connections so as to minimize this error or loss. Now, these weights and biases actually affect which features neural network extracts from the image and the importance to them it assigns. And so that's how it works. A neural network is basically like an end-to-end feature extractor and classifier built into one network as compared to the statistical method. And bring your attention back to transfer learning. It's actually a process whereby we leverage on a model already pre-trained on extracting general features and fine-tune it to our use case. A model like ResNet 50, MobileNet, or EfficientNet, already pre-trained on huge dataset of multiple classes, can tell you whether an image is a spoon, a cat, or a dog. And this is actually because their weights and biases have already been adjusted to recognize the key features, such as maybe eyebrows, the shape, the nose, that help discern between these image classes. In general, the earlier layers of a neural network, that is the layers at the left side, they are kind of trained to recognize more general features such as contours, edges, maybe gradients, and deeper layers, the ones to the right, are more trained to recognize more specific features such as how the from the previous layer, such as how the shapes, the gradients, the contours come together to form nose, eyes, and stuff. And even deeper layers take all this information from the previous layer, such as the nose, eyes, and everything, and try to position them and try and form a face. So that's what is meant by recognizing more general to less general, or rather less specific to more specific features across the neural network. And in transfer learning, we want to exploit that by taking a pre-trained model and keeping all their weights, which is known as freezing the network, and replacing the classifier layer with our own one, with our own fixed number of classes. Because usually these pre-trained models have a classifier layer with like hundreds of outputs, one for each class, maybe a spoon, dog, cat, fish, mouse, etc. So we want to take away that classifier layer and replace it with our own, with our fixed number of outputs, maybe 2 or 3 outputs, one for each class. Maybe we just want to discern between a dog and a cat, we will just have 2 outputs. The probability of each output giving us the probability that the image belongs to a certain class. And so the process of transfer learning is as follows. We take a base pre-trained model, freeze the model, which means we prevent the model weights from being updated during backpropagation in training, and we replace the classifier head with our own. Now, during training, the weights of the connections between the layer before the classifier and the classifier, they are updated. So basically this red arrow here, which you can think of as weights, which connect every, think of as the connections that connect every output from the previous layer to the classifier, because the classifier layer is essentially a fully connected layer. And so during the training, the weights of these connections are updated to minimize the error or loss function, whereas the ones before them are not updated because they are frozen. So then after this, we compile, we train, and then we evaluate the model. And as you probably noticed, there are very few, relatively few connections here compared to the whole network. And therefore, we don't really need much training data to get to reach the optimal. And here is the code taken from the TensorFlow documentation. So over here, we just import the MobileNet V2 model, we initialize it. We set include top to false, and top, as you think, as you know, it means the classifier layer because it's at the top of the network, which is classifier. So we set the whole model to be false, the trainable to be false, and then we replace the classifier head with our own number of outputs. This code you can probably find on, or you can find on the TensorFlow documentation. It's very comprehensive there. So this is just a little short summary, just the gist of it. So this is one way. And sometimes when we do it this way, where we freeze the entire network and we just replace the classifier layer, the results may not be very good. The performance may not be very good. So especially if you want to classify things that are not maybe, maybe they share a lot of similarities with the data set that our base pre-trained model has been trained on, but there are some specific features that are not accounted for. For instance, in our alien versus predator model, the heads of the aliens and the predators are drastically different from those of humans. Not really drastically different, but in terms of like the shape, they're different, but the major facial features might be there. So here, there's another way where we do not freeze the entire model. We just freeze maybe the first 100 layers and leave the remaining maybe 50 layers unfrozen or 20 layers. And the reason we do this is because, as described earlier, the first the earlier layers of the neural network are kind of responsible for discerning these very general features like contours and nose and stuff, whereas the later layers are more for specific features, such as how all of these contours, how all of these nose, eyes, and stuff come together to form more specific features like a face in some sense. So we, instead of freezing the whole model, we just freeze the first 100 layers and we leave the rest trainable. That is, the weights can be updated during backpropagation. We also replace the classifier head as described earlier to fit our number of output classes. And then we train it. We train it using our training data set. And all the weights here, which are trainable, which are unfrozen, can be updated to minimize the loss. Whereas the layers which are frozen, they do not get updated. They just stay as they are. So this way, we can really exploit the knowledge of our pre-trained model to suit our task. And this is what is known as fine-tuning. in transfer learning. Here's the accompanying code, once again, from the TensorFlow documentation. Here we first set we set the whole model to be trainable, right? And then we freeze the layers, starting from the leftmost all the way to the rightmost, starting from the earliest to the later, the most shallow to the deeper layers. So here we just iterate through the layer from the 0th layer all the way to the 100th one, and we freeze it by setting it to be false, trainable to be false. And once again, freezing it means that we do not let the weights be updated during training. And then we replace the classification head, and we compile, train, and evaluate. So the process is pretty similar. So finally, relating it to our initial base defense problem, as we don't have to train every single weight of the model from scratch, just the ones between like the final layers that we have unfrozen, we don't really need as much data as before, and can probably work with the small data set we have from our CCTVs. And that is how transfer learning saves the day. And this is also why most people use transfer learning for their problems. It's because transfer learning doesn't require, I guess, as much data as if you were to train the whole model from scratch, because we're essentially training fewer connections. And we're leveraging on the huge amount of information that it already possesses for the general features. And this is why transfer learning is very widely applied in the world. It might come in handy, it might not for your current, the chip counting problem, depending on whether you can find suitable pre-trained models to apply on that chip training problem. But as mentioned by Rama, we probably need a mix of both computer vision and deep learning techniques. And for a more realistic example, relating it to our, for a more realistic example, you can check out our previous workshop on building an end-to-end face mask detector application. Transfer learning was used here to build the model where we fine-tune a pre-trained model to detect a mask on the face. We just use something that can detect the faces. We try to train it. We unfroze some of the layers and we fine-tune it with the face mask data set that we obtain through data augmentation. Yeah, and last but not least, here are some very helpful resources. First is Andrew Ng, very famous machine learning guy. You can watch his video for more intuition and theory on transfer learning. The next one will be the TensorFlow documentation that you will probably have to refer to all the time if you want to code anything in Keras and TensorFlow. The next one is just a Google search for Kaggle. Well, I just put in Kaggle transfer learning there. It has very helpful notebooks where you can see how other people apply transfer learning techniques to solve Kaggle competitions, which you can probably just copy half of their notebook and solve our competition and maybe just fine tune it and something like that, which is actually what most people do on Kaggle. For the next one is a more in-depth understanding on actually how many layers to freeze of the model, of our of the pre-trained model when you do transfer learning. Do you freeze like 30% of the layers? Do you freeze 70%? Do you just leave everything frozen? Or what do you do? So this link helps you understand or approximate how many layers to freeze for your use case. The next one would be the Alien versus Predator transfer learning project that I come across online. I think it's pretty interesting to read. And lastly, it's our face mask workshop that you can take a look. There's also a YouTube video on the link there, which you can watch for deeper insight on how we kind of build it end to end. Because we not only covered like the machine learning, how we built the machine learning model, but also the web application itself. And that would do it for my part. Thanks.
Yeah, so thank you, Georgie. So hold on, let me try and share my screen. Give me a second. Yes, so thank you, Georgie. So now that all of you have learned about classical techniques in computer vision, through an introduction about deep learning-based methods and the intuition behind CNN architectures, and then finally, an example of how to apply such networks in a more practical setting using transfer learning. I would just like to wrap up this session by recommending a list of more practical tools, frameworks, and resources that you might find useful. And these resources that I introduced will be more specific to building machine learning pipelines and solutions. Right, so first of all are tools for experiment tracking. So I think as a data science practitioner, you might find yourself conducting a lot of experiments iteratively, and you may even lose track of what you've changed between each experiment, as well as the effects of each change, right? And you may wonder, how can one actually manage these experiments in a more organized manner? So, like, while, the folks over at software development have mostly figured this out through building tools that keep a historical log of changes through version control. Data scientists, I think, for the most part, unfortunately, do not have the same luxury until much recently, where we now have applications such as weights and biases and Comet ML that do experiment tracking. So these tools allow you to keep track of multiple runs and to log training curves, hyperparameters, evaluation metrics, model weights, notes, and more. And this is all done just by adding a few lines of code to your code base. And like best of all, most of these frameworks can be hosted on the cloud, so you can conveniently track experiments even if you're away from the machine, and even collaborate as a team and have all your team members contribute to this same dashboard and log all your experiments to the same platform. Okay. Yeah. So now that you have the ability to easily keep track of your experiments and hyperparameters, you may wonder if there actually exists a tool that can help you choose these hyperparameters automatically. So when I say hyperparameters, I refer to the various design choices that you make when building your model pipeline. So for example, this might be the number of layers in your model, the learning rate in your optimizer, or even the different pre-processing steps that you do to an image before feeding it to your model. And you may sometimes feel that this hyperparameter choices are arbitrary, or that there are way too many knobs to adjust during training. So yes, there are many options for automated hyperparameter tuning. So this includes frameworks more specific to Keras like HyperRAS and Keras Tuner, and also more generic frameworks like HyperOpt and Bayesian optimization that basically employ more sophisticated methods that so it performs more extensive experimentation to maximize your objective more intelligently than, let's say, brute force hyperparameter search. Yeah, so how do you use such frameworks? So this is actually as easy as, hold on, right? So all I have to do is you first start out by defining your hyperparameter search space. So for example, so you want to search, specify the number of layers to models to be, let's say, I want to search between 1 and 3, or you want the dropout rate to be between 0 and 0.5. So after specifying this hyperparameter search space, you can just define a function that takes in these hyperparameters and outputs your model. And yeah, and then after specifying how many trials or how many different hyperparameter choices you like to experiment with, that you like to run based on your available computing budget, you can just finally leave it up to the framework to do the rest of the heavy lifting. Right, so you'll find the best hyperparameter setting for you based on your problem task. Yeah, so if you like to go one step further and you think that, oh, I'm too lazy to even attempt to define my hyperparameter search space, or you think that you don't have the domain expertise or any expert knowledge to be able to make an informed choice, right? Then you can resort to AutoML. So AutoML, like the name suggests, employs something called neural architecture search. So it's an algorithm that helps to find the best architecture for you, basically. And this can be accomplished through packages like AutoKeras or AdaNet. And with such frameworks, you only need to specify the high-level architecture of your model, and the framework will just search for the best, more detailed configuration for you. So for example, this library called AdaNet provides a general framework to not only learn a neural network architecture, but also to learn an ensemble, right? So a collection of neural networks that in which you can combine all their predictive power to perform better on your own problem tasks. So so just to give you a quick impression of how such algorithms work. So as the following GIF shows, AdaNet will adaptively grow an ensemble of new networks. And so at each iteration, it will measure the loss for each candidate and select the best one to move on to the next iteration. Yeah. So I personally haven't tried out this method before, but so I can't really vouch for them, but I think it'll be interesting to give it a try. Right. So next is where to find model. So Georgie introduced the concept of transfer learning, right? And how you can utilize a pre-trained model, a model where some other guy out there has already trained using a specific and typically large data set and using his own computational resources, and then fine-tuning that on your own task. And you may wonder how do you actually go about searching for such models? And the answer is that such models are typically open source and are in fact very easily searchable and accessible online. So for example, there's this website called Papers with Code that basically builds up a compilation of all the available papers out there and organizes them by the task, the domain task, and also the specific task. Yeah, so for example, within computer vision, you have tasks like image classification, semantic segmentation, object detection, etc. So let's say you like to find like a model for image classification. You can head on to this, click on this, and you'll see that Papers with Code has organized all the models by benchmarks. So it's organized by a data set. So let's say you're interested in a model that can do well on this image set data set. You can click on this, and it will not only, so what you see here is a leaderboard of all the models that have been evaluated on this image net data set and its corresponding evaluation metric. So this can be a starting point to which to search for a model, similar model for your own task. Right. So like for example, I can just, say I'm interested in this paper, I can click on it, and most of the time, Papers with Code will link to either the official or unofficial implementations of this paper. So you can just click on it and check it out. So really it's a matter of like, going to these GitHub repos, looking at their README file, and then finding a way to understand the API and to integrate them into your own code base. Yeah. And you can also find lists of other models out there through these links. Yeah, so it's not, yeah. All right, so next important thing that I like to talk about is where to find data sets. So for machine learning, labeled data sets are the field for your model, right? In most cases, if you have a large enough and suitable training data set for your task, you can easily leave the rest of the heavy lifting to your powerful machine learning model to learn how to do your prediction tasks. So as to where to find publicly available labeled data sets, there's actually many comprehensive data set indexes out there. So for example, you can just head on to this search engine, data set search engine by Google, and search for your desired data set. So for example, I want label data set of fashion images. I'll do a fashion classification task. You can just search and browse through this list. And then more specific to computer vision, there are also specialized websites like Visual Data, Bifrost, that so they compile data sets produced by researchers or by other people, and they have to organize it by the task and also by what images do these data sets contain. So again, if I like to search for fashion images, I can just search for fashion and take a look at this list. And so I'm interested in image classification, right? So I might check out the data set like this. Okay. Yeah, so other than this publicly available data sets out there, you might also want to create your own data sets, so DIY. And I've just listed some links over here they can check out. So for example, you can easily download the assets of Google Image Search through like this plugin. There's a command line interface if you want to do that. And there are also other like graphical interfaces in which you can do the same thing, right? Scrape images off the internet. So alternatively, you can, if you're more programmatically inclined, you can use something like more like heavyweight library like Scrapey to do your own like specialized scraping tasks. Okay. Yeah. So lastly, if you like to keep up with state-of-the-art or cutting-edge methods, you can check out these few resources. So realistically, you don't really have to keep up with state-of-the-art or religiously, unless you're a researcher working in a specific field, or if you're really like trying to squeeze out a few extra points out of a Kaggle compilation. But in the case that you like to do so, so again, Papers with Code is a good way to keep up with state-of-the-art, as like I've shown, it maintains this like leaderboard for various dataset benchmarks. And like as you can see over this graph over here, it tracks the advancements and the evaluation metrics over the course of different papers. And you can also check out the search engine for academic publications like Semantic Scholar to look for citations or references of a specific paper. So for example, if I'm interested in this paper called Deep Residential Learning for Image Recognition, I can check out the references. Yeah, in order to find out what works came before, or I can also check out the citations to find out what works have built upon this specific technique in order to achieve better results. Yeah, and alternatively, there's also this website called Connected Papers, where you can specify a paper, and it will use some algorithm to build up this like graph of rated papers, where you can then explore it like interactively through this graphical interface. So this is another cool resource you can check out. Okay. So yeah, that will be the end of our workshop. So just like as a brief recap, we went through classical techniques and computer vision, to introduction about deep learning based methods and the intuition behind TNNs, and why you might use such architectures for images. And finally, an example of how to apply such networks in the practical setting using transfer learning. Okay. Yeah, so these are some of the references we use in when building our slides that we encourage you all to check out. Okay. Yeah. So before we end this session, just something I'll point out is, so the purpose of the workshop is just to provide a general overview of computer vision. And the methods that we introduce or talked about may or may not necessarily be suitable for this competition. So there's probably a host of other different ways, not necessarily like learning-based methods to approach this problem. And I think it's up to you as participants to come up with your own creative ideas. And my general advice would be to focus more on constructing a robust solution to this problem task. So yeah, I just hope you have fun and learn a lot through this competition.
All right, thanks a lot, Yizhe, Georgie, Rama, and Agatha. So just a heads up again, there is another DSC workshop by Up Level using computer vision for object detection and counting. And this will be specific for the tasks related to the competition that we have. So do note that the workshop will be on 18 January, 7 p.m. to 9:30 p.m. You can learn more about Up Level on the link below here. I'd like to give a shout out to the next few workshops that NUS Statistics Society also have planned for semester 2, which is the Effective Data Storytelling workshop on Wednesday, 27 Jan, 6:30 p.m. to 8 p.m., as well as Using Tidyverse in R for Data Analysis and Visualization by Sanraj and Jianhui from Statistics Society. To learn more, do take a look at our Statistics Society website down below. Now, thank you very much for joining us in this workshop, and we hope that you have enjoyed yourself, you have learned a lot from this workshop, and do fill in the feedback form for us so that we can be prepared for our subsequent workshops. Thank you very much. These are our contact, and we will stay in the chat if you have any questions. Hello. All right. Yeah. The workshops will be uploaded. The videos will be saved, and all the workshop resources will be available at the Statistics Society website. You can see over here. So you just click this link and then go and click workshops, and then there should be a list of all the resources down below. Yeah, if you have any last questions, just put them in the YouTube chat here. Otherwise, we will close at about 9:12 p.m. All right, once again, thank you so much for joining our workshop, and thanks again to the presenters, Ita, Rama, Georgie, Agatha, who have been working hard to deliver this workshop to you as best as they can. I'm sure they were super nervous about presenting, so do shout out your appreciation for them in the chat if you can. Yeah, once again, we'll appreciate your feedback on our workshop so we know how you feel about our workshop, we treat the feedback very seriously and aim to improve on all our future workshops to bring you a great experience in our workshops. So our social links are available below. So do check out, especially the Telegram channel, where we post about some articles sometimes. Yeah. Otherwise, thank you very much and all the best participants for the competition.